Okay, now we move on to Chapter 8, Chemical Equilibrium. I'm going to break this up into 4 sections. The first section is looking at a bit of the theory behind reversible reactions and the nature of chemical equilibrium. So first of all, reversible reactions. Now we're looking at reactions here which don't go all the way to produce all the product. So what we see for a reaction like the Haber reaction between nitrogen and hydrogen to produce ammonia, we know that this reaction goes, it's a very important reaction, we make lots of ammonia this way. But what we also need to recognise is that the exact reverse reaction also occurs. Ammonia decomposes into nitrogen and hydrogen. And in any sample of a gas at a sufficiently high temperature and pressure for the reaction to occur in the first place, both reactions will be going at the same time. So the way we indicate a reaction like this is with a double-headed arrow. That indicates a reversible reaction. If ever you see that, you know that this is an equilibrium situation. If you've got a reaction that is an equilibrium situation, you always have to include the double-headed arrow. So we've got both reactions occurring at the same time. So we've got nitrogen and hydrogen reacting to form ammonia. We've got ammonia decomposing to form nitrogen and hydrogen. Two competing reactions. Now, at some point, they're going to reach a stage where they're in just a position they exactly cancel each other out. So this is going to occur when the rate of the forward reaction is exactly equal to the rate of the reverse reaction. The rates are in balance. We say the system is at equilibrium. Graphs are very important in this topic. Again, the first thing we do is look to see what's being measured. In this case, it's concentration, how the concentration of each of the 3 reactants varies over time. Now, what's our initial state? So initially, we've got 3 moles of nitrogen and hydrogen, no moles of ammonia. So that looks like the experimenter added some nitrogen and hydrogen to their vessel and let them react together. So the first thing that happens is we see a reasonably steep graph for the production of ammonia, reasonably steep graphs for the drop in concentration for the consumption of nitrogen and hydrogen. We see hydrogen dropping more sharply than nitrogen. Why is that the case? Well, have a look at the equation and you'll see there are 3 moles of hydrogen being consumed for every 1 mole of nitrogen. Over time, what happens is, as we get more and more ammonia, the reverse reaction starts off, and so the overall rate of production of ammonia slows down. And it gets to the point where the concentrations remain constant. And that's what we look for in one of these graphs, to know that the system is at equilibrium. If concentrations are constant, the system is at equilibrium. So let's look at this in terms of collision theory. And at the end of the day, I think it's the collision theory, particles colliding, which is probably the best way. If you can get your head around this, it's the best way to understand equilibrium. So initially, only nitrogen and hydrogen are present in the vessel. So we've got a high frequency of collision between the reactant particles. That means the rate of the forward reaction is going to be at its highest at this point. The reverse reaction is not occurring at all because we don't have any product initially. So we get the rapid increase in nitrogen and hydrogen, rapid decrease in nitrogen and hydrogen, rapid increase in ammonia. Now, of course, straight away ammonia is being produced. So as soon as you get a significant amount of ammonia, you've got a significant reverse reaction beginning. And at first it's going to be slow because not much ammonia means few collisions. But as time goes on, more and more ammonia gets produced, the reverse reaction speeds up, less and less nitrogen and hydrogen are present, the forward reaction slows down. And that's going to continue until the point of equilibrium occurs, when the rate of the forward reaction is exactly the same as the rate of the reverse reaction. The reactions cancel each other out exactly. So at this point, both of the reactions are still occurring. They're just cancelling each other out. So it's not as if the reaction stops. Both reactions occur. So while looking at it from the outside, it appears nothing is happening. In reality, a lot is still happening. The reactions are still going and cancelling each other out. That's why we call it a dynamic equilibrium. The rates of the forward and reverse reactions are equal. So if you're looking at that system from the outside, all the external features of the reaction system are going to be unchanged. So the concentration, temperature, pressure are going to remain constant with that system at equilibrium. And examples of reversible reactions. You can look at, obviously there are the classic chemical reactions, production of ammonia, production of sulfuric acid, but even physical processes like boiling water can be thought of as an equilibrium situation. It's a reversible reaction that can reach equilibrium, but it can only reach equilibrium if we've got a closed system, if we stop the water vapour escaping. So if we've got a sealed vessel with water in it, there's, at any temperature below 100 degrees, there is going to be both liquid water and water vapour. And if it's, like I say, if it's a sealed vessel, that water vapour is going to reach a constant value at some point. That is known as the vapour pressure of water at that particular temperature. Rechargeable batteries, the lead acid battery that you've seen in one of the previous chapters. It's a reversible reaction, but it doesn't actually reach equilibrium because the activation energy to reverse it is too high. You've got to pump a voltage in before that one will go backwards. Oxidation of SO2 in the sulfuric acid production, that's another classic equilibrium situation. So just be aware of what we mean by different sorts of systems. Normally, if we do a chemical reaction on the bench in a beaker, often it is an open system, especially if it involves a gas. The gas can escape, so mass can come and go from that reaction. An open system allows exchange of energy and of mass with the environment. A closed system keeps all the chemicals in one spot, prevents chemicals from escaping, but still allows energy to move in or out of the system. An isolated system, on the other hand, doesn't even allow energy to come or go. And that's the end of this little bit.